Assalamualaikum. Today we're gonna explain about Synchronous abnormal counter. This slide presented by Nadia, Anis and Farah. This is our group members. Me, Nur Farah Shazwani binti Azman.
My name is Nur Nadia Tunazira binti Mazarizi.
My name is Anis Afika Syahira binti Mazlan.
Next is introduction. This picture shows a special type of counter. It's called a synchronous abnormal counter. It used for JK flip-flop and some logic gate. Unlike normal counter that count up or down, this one counter is a special custom order. All parts get the clock signal at the same time, which make it work very precisely. This is good for time when you need a specific non-standard counting pattern. Next is objective. The objective for this project is to design a 7-state 4-bit synchronous abnormal counter using JK flip-flop. To implement the counter using multi-sim software or equivalent digital circuit simulation software and observe its output using a 7-statement display. Last one is to present the finding and submit the multi-sim simulation file along with this report. Next is convert to binary. Our synchronous counter is designed to follow a specific 7-state abnormal sequence. In hexadecimal, this sequence is 2, A, 4, 3, C, 0, and 1. For state 1, in hexadecimal is 2. In binary, will be 0010. State 2 hexadecimal is A. In binary it will be 1010. And for state 3 in hexadecimal is 4. It will be 0100. In state 4 hexadecimal is 3. It will be 0011. In state 5 hexadecimal is C. Binary is 1100. In state 6, hexadecimal is 0. In binary will be 0000. And the last one is state 7. Hexadecimal is 1 and binary will be 0001.
Next is excitation table. This excitation table provides the necessary information to complete the state table. To design a synchronous counter, we need to determine the required input for each flip-flop for every transition in our sequence. We achieve this by utilizing the JK flip-flop excitation table. As you can see from the table, for a given present state Qn and next state Qn plus 1, it specifies the necessary JK input. For example, if the present state is 0 and the next state is 0, J is 0 and K is X. Okay, next, continue to state table. This is our state table that show how the counter transition from one state to the next. It also include the necessary input for each JK flip-flop. In the table, we have several X value. This represent don't care condition, meaning the value can be either 0 or 1 without affecting the output. This helps simply logic later during K-map reduction. Okay, next, continue to Carnot map and Boolean expression. We have the Carnot map for the J3 input. We populate this K-map using the corresponding J3 values from our excitation table. By grouping the cell, we derive the simplified Boolean expression for J3. The output clearly show that J3 simplified to Q1. This means the J input of the third flip-flop will be directly connected to the Q output of the first flip-flop. Next, this Carnot map is for our K3 input. After mapping the first and X from our agitation table onto the K-map, we identify groupings for adjacent one is or x to simplify the expression. As you can see from the grouping, the most simplified expression for K is 1, which means K3 will be connected directly to VCC or a high voltage source in the circuit.
Here we have the K-map for the J2 input. We derive the 1, 0 and x from our complete excitation table, which is particularly shown here for reference. In this K-map, we identify two primary groupings. Their grouping allow us to simplify the Boolean expression for J2. The result simplified expression for J2 is Q3 plus Q1 multiplied Q0. This means that the J input for our second flip-flop will be determined by the logic OR of Q3 and the logic AND for Q1 and Q0. This slide displays the K-map for our K2 input. As you can see, after placing the value for our expression table, we have numbered x, condition and sum first. By grouping all the 1 and don't care as shown by the large circle, the expression for K2 simplified to a context 1. This means that the K input out for our second flip-flop K2 will be permanently connected to VCC or a high logic level in our circuit design.
Next, I'm going to present about Carnot map and Boolean expression for K1. Here we have the K-map for K1. Through the identified groupings, the simplified expression for K1 is Q3 plus Q3 bar multiplied by Q0. This means K1 is the logical O of Q3 and the N of Q3 bar complement and Q0. Next, here we have the K-map for J0. Through the identified groupings, the simplified expression for K0 is Q3 bar and Q1 bar. This means J0 is the logical OR, use a logical OR gate. Next is Carnot map and Boolean expression for K0. The output get 1. Next is simulation circuit. This slide shows the full circuit diagram of our synchronous abnormal counter design and simulated in multisim. The circuit overview. 7-state synchronous abnormal counter simulated in multisim. Designed with 4 JK flip-flop synchronously clocked. The next is logic gate control input for custom counting. Output display on 7 segment for verification. Next is result and discussion. 7-state synchronous abnormal counter successfully tested using multisim. Utilize 4 JK flip-flop and logic gate for a unique counting sequence. Accurately followed sequence 2A43C01 with distinct 7-segment display output. Carnot map effectively simplified logic and reduced gate count. Simulation confirmed successful operation and meet project objective.
Okay, the next conclusion. The 7-state synchronous abnormal counter built with JK flip-flop successfully achieved its objective through a systematic design process. The circuit accurately transitioned through a defined sequence 2A43C01 as confirmed by multisim simulation. This project not only demonstrates the reliability of synchronous counter for specialist digital application but also significantly exchange our practical understanding of sequential logic design. Okay, next. Thank you for listening.